Hello, Honors Chemistry, and welcome to a quick overview of part of Chapter 12, where we're just going to highlight some of the notes from evaporation, condensation, melting, freezing, and then do a little bit of math together. All right, so first of all, we should all be comfortable with the concept of evaporation because it's one of those things we all have some life experience with, right? So obviously, if any vessel is open, right, left open to the environment, and there is a liquid inside over the course of time, what happens? Right, it's going to evaporate, right? Meaning that even at room temp, even at freezing, right, or just above freezing, because that's the only time it would be liquid, right? Some of these molecules have enough kinetic energy that they are able to escape the liquid phase, right? So they are able to overcome the attractions between each other such that they have enough energy to go into the gaseous phase, right? And those molecules leave, and because the vessel is open, they are able to escape, become part of the atmosphere, and not come back, right? And obviously, the longer it sits there open, right, it will continue to do that. There is a net evaporation. So over the course of time, if you leave a glass of water out and open, over the course of a week or so, it will all be gone eventually, right? Which is one of those live things we all know. Now, we have a different scenario if my vessel is sealed, right? Again, at room temperature, there is enough energy that some of these molecules have enough energy to enter the vapor phase, right? Which means that over the course of time, right, this part up here, even if it's evacuated first, will become saturated with H2O gas, right? Meaning that over every liquid, there is always some gaseous form of that liquid present, right? Which goes back to what vapor pressure is, another one of those chapter 12 topics. Anyway, evaporation will continue, but once there's enough gas built up, right, we do get some condensation, right? So some coming back to the liquid, some liquid still becoming gas, and eventually we reach this wonderful place called dynamic equilibrium, where macroscopically there is no further change, right? With our eyes, we won't see the level of the water change, right? If we were measuring the pressure, we would get no more change in pressure. But, right, and that's what equilibrium means macroscopically. Microscopically, this is what it means, right? The rate of evaporation is equal to the rate of condensation, meaning that the same number of particles that are escaping into the gas phase is equal to the number of particles going back to the liquid phase, right? And since it is constantly moving, just the total amount doesn't change. That's why it's called dynamic equilibrium, right? Equilibrium meaning the place where macroscopically there's no more change, right? But things are still moving, right? So, we would never say that microscopically everything is done, right? Because there is constant change happening at the microscopic level, okay? All right, that brings us to the concept of heating curves. So these are two different figures from your textbook taken and sort of mashed together, right? So here in this first figure, this is what happens when we take ice. So we would have ice down here. And when we add, so heat added, versus, and up here we have our temperature change. So we're adding a consistent amount of heat. So anytime we're looking at heating curves, right, it needs to be noted that the amount of heat added is constant per unit of time, right? In that this would be like sitting on a hot plate or over a Bunsen burner at a constant heat input. So we wouldn't change the knob, right? So if it were on our stove, this would be a pot of water or ice that we put on heat setting 3 and we left there, right? As we monitored the change in temperature. Okay, so if we had our bucket of ice and we put it on our stove at a setting of 3, for example, eventually that ice is going to slowly but surely absorb some of that energy, and the molecules will move faster and faster and faster, and they'll vibrate more and more and more until at about 0 degrees, some of those molecules now have enough kinetic energy that they can break loose from the solid crystal structure so that we can get some free flowing liquid molecules, right? And note that once we get to 0 degrees Celsius, what happens to the temperature here? Right, temperature stops changing, but we are still adding heat, right? Super important. At 0 degrees Celsius, so at the melting point, we are still adding heat, but the temperature no longer changes until all of it melts, right? So here we would have a solid, here we have solid and liquid, okay? So they exist together during the melting process. Temperature does not change because all heat at that point is going into breaking attractions between molecules, okay? At the melting point, all heat is going into breaking attractions between the molecules. And once all those attractions have been broken such that now it's complete liquid, now again the temperature can go up, right? Because now we're just increasing the kinetic energy of our molecules, how fast they move past one another, until eventually we get to 100 degrees Celsius, and what happens there? Boiling, right? So here, again, we get another plateau in temperature in that we are still adding heat, right? So this would be like saying we're still at heat setting 3. But again, now we are putting energy in, no change in temperature, because we are breaking the attractions between my liquid molecules, right? We are breaking that last bit of attraction so that they can escape into the gas phase where we assume what? Right, that there are no attractive forces present. So at this point, we are breaking all attractive forces such that they are independent molecules that no longer interact with one another. Yes? All right, so putting that all together, that gives us this figure from your book, right? Giving it some important labels. All right, so here, right, again, going back to our states, right, here we have solid, here we have a liquid, and here we have a gas, right? So we would say that we are heating a solid, heating a liquid, heating a gas at that point in our graph, right? Down here at this plateau, this is the act of melting, and this plateau is the act of boiling, okay? So these correspond to those respective points. So how do we determine how much heat is required to heat to increase the temperature of my liquid? Right, that goes back several chapters to the specific heat of a liquid, which for water, because this is water, 4.184 joules per grams times degrees Celsius, right? Heating a solid has its own, C being a C of solid, gas has its own C of gas, okay? Now, for the actual phase changes, for boiling, we have our heat of vaporization. So this is the amount of energy needed to vaporize. Melting has a delta H of fusion, which is the amount of heat necessary to melt something. Yes? All right, so then if we wanted to calculate the amount of energy required to go from one temperature to another, right, like let's say from -25 to say 50, we would need to add together all the respective parts, right? So first we are heating a solid, then we are melting our ice, then we are heating a liquid. So there would have to be 1, 2, 3 separate pieces of math that we would sum together to come up with our final answer. Yes, does that make sense? And no worries, you will do some practice soon. Oh, look, practice. Okay, so let's do some of these together. So it says to calculate the amount of heat in kilojoules required to vaporize, right? So if I'm trying to vaporize water, I know that I'm going to need my heat of vaporization, which for water, at its boiling point, we would go look at that chart. You're not expected to have it memorized. So heat of vaporization of water at its boiling point is 40.7 kilojoules per mole. And here is the amount of water. So we need a heat in kilojoules, right? This converts between what two quantities? Right, heat and moles. So once we have moles, we can use that conversion factor to get to heat. Can I get to moles? Absolutely. I have a grams, and I can get to moles using, ding, 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 molar mass. So 2.58 kilograms of water. Nope, that's definitely grams of water. And I know that 18.02 grams of water for every 1 mole of water. I also know that there are 1,000 kilograms per gram. And finally, I also know that for every 1 mole of water, I require 40.7 kilojoules of heat. Yes? And that is going to give us the answer to this question. Make sense? All right. Next question says, a drop of water weighing this many grams condenses on the surface of a 55-gram block of aluminum that is initially at 25. If the heat released during condensation goes only toward heating the metal, what is the final T in degrees Celsius of the metal block, right? So I would like to know the final T of my metal block. Oh, by the way, this is the T of my metal. No, not the T. That is the specific heat of my metal. And I know that this is the heat of vaporization of water, okay? So what's this problem really asking us to do? Right, there are two things happening. So one, we have our condensation. And we know that condensation releases energy, right? So we need to figure out how much energy is released because all of that energy goes into, right, the metal, okay? So step number one, we need to figure out how much energy is released. So if we have 0.48 grams of water, And I know that there are 18.02 grams for every 1 mole of water. And I know that for every 1 mole of water, 40.7 kilojoules of energy are released, right? So this is what's going to give us the amount of heat released. 1.08 kilojoules of heat released. And where does all of that go? Right, that goes into the metal block. I would like to know the final temperature. Does that sound familiar? Right, that goes back a couple of chapters again, where we have this equation, right? Q equals mc delta T, right? This is what? Right, this is the Q. This is, so 1080 joules are absorbed by that metal block. That metal block has a mass of 55 grams and has a specific heat of 0.903 joules per grams degrees Celsius. And I know that I have T final minus T initial, which is 25 degrees Celsius, right? So once I solve for T final, that's what's going to give us our answer. Yes? Make sense? All right, next problem. Calculate the amount of heat absorbed when 15.5 grams of ice melts at 0 degrees Celsius. So this is just like that first problem we did on the other page, right? Where if I have 15.5 grams of ice, I know, and I could say ice here, I guess, to be specific, right? I know that for every 18.02 grams of ice, I have 1 mole of ice. And I know that, and again, you wouldn't have to memorize it, you would just go look it up in a chart, or I would give it to you in the problem. But if I want to talk about melting and heat, what constant do I need? Right, I need the heat of fusion, which is 6.02 kilojoules per mole. So for every 1 mole of ice, 6.02 kilojoules. Yes? All right, next up, a 5.6 gram ice cube at 0 is placed into 195 grams of water at 25. If the heat absorbed for melting the ice comes only from the water, what is the temperature change of my water? So first, what do we need to do? Right, this is just like this problem where there are 2 separate pieces, right? So first we need to figure out how much energy that ice is going to require. So we would have to start with our 5.6 grams of ice, and we know that, again, 18.02 grams of ice for every 1 mole of ice, and then I know that for 1 mole I would require 6.02 kilojoules. So this math would be 1.87, I think, kilojoules, right? And that's the amount of heat needed. And we're going to take that heat from, right, that 195 grams of liquid water, right? So we're going to get 1870 joules from that liquid water. And is it going to go into or out of the water? Right. Out of the water, right? And its mass is 195 grams. And of course we memorized this is 4.184 joules per grams degrees Celsius. And then we just need to solve for delta T of my water. Yes? Make sense? All right. Thank you for listening. Be good, and I will see you soon. Bye.